Okay, let's talk through the Thor's hammer problem. So, first we need to recognize Thor is standing on the edge of a cliff that is 70 meters high. Thor is spinning the hammer above his head. The strap handle has a length of 0.8 meters. Okay, so I'm going to record that. I'm going to say that the length, which I'm going to represent as R, is going to be 0.8 meters. When Thor lets go of the spinning hammer, the hammer was experiencing a centripetal force, so force centripetal of 12 times by 10 to the 6th newtons. How fast was the hammer going if it had a mass of 60? So we want to know what that linear velocity is, and we know that the mass of the hammer is 60 kilograms. Okay, wonderful. All right, so we need to pick an equation where we know everything except for the unknown. Okay, and so we have this interesting force centripetal, and one of these centripetal force equations is this one. Okay, now, force centripetal is equal to the mass of the object, the linear velocity squared over that radius, right? Because if it's spinning, that like distance from the center out. And we know this, we know that, we know the mass, we're solving for the velocity. So I need to rearrange this equation to solve for that velocity. So the first thing I'm going to do is I'm going to multiply by r to both sides. So I will have r multiplied by force centripetal equals mass velocity squared. Then I will divide by the mass. Oh, and that would give me my velocity squared. And then the last thing, I'll take the square root of both sides because I'm not solving for the squared velocity, I'm just solving for the velocity. This whole thing is being squared, the square root. And that will equal the velocity. Okay, couple things to note and to keep in mind. If I'm not going to rewrite this equation with all my numbers, that's fine, and I almost prefer it that way, but you have to give me this list. Somewhere in your work, you have to show me that you recognize what R is, what the force centripetal is, and what the mass is that you're talking about. And then I'd plug this all in my calculator. I would be mindful and careful of my parentheses, recognizing that this whole thing, I'm taking the square root of the entire thing, and I'm going to keep this on the top of my fraction, that on the bottom. And so I'll plug that in, and I get a final answer of 400 meters per second. Okay, if you're following along with me, you really might want to consider hitting pause, plugging these numbers into your calculator, and seeing if you got the same thing. Half the battle sometimes is just recognizing and knowing how to plug it into our calculator. So that's my first answer for part A there. Spinning a hammer above his head, the strap handle has a length of 0.8 meters. When Thor lets go of the spinning hammer, the hammer was experiencing a centripetal force of that much. How fast is the hammer going? And so that's our how fast. Okay, part B. How far did the hammer travel up in the y direction if he throws it at a 20-degree angle above the base of the cliff? Assume no air resistance. So a reminder, he's standing on a cliff, and he's going to throw this hammer at an angle now. So it's angle, it's going to come up, and then eventually it's going to come back down and hit the ground, right? Okay. I think there's two possible answers here. He said, how far did it travel in the y direction? And you could say, well, if it started here, then this would be the y direction. Better wording that I could have used would be, what is the maximum height of the hammer? And that would be at the top of the arc here. Because really what I'm wanting to know is, what is this total displacement of y from the ground? Okay, I want to know that height at the top of the arc there. So a couple things. We need to know this initial velocity, which we do, it's 400, but there is an x component and there is a y component to this. So if I were to zoom in on what's happening right there, I'd say I had a velocity of 400 meters per second. And this 400 meters per second can be broken into velocity in the y direction and velocity in the x direction. And in the problem, it says if he throws it at a 20-degree angle above the base of the cliff, like a 20-degree angle above horizontal would be better wording there. A 20-degree angle. And then I'm just going to use trig to get that velocity in the y and velocity in the x. Because if I want this component, it is opposite from my angle, and then I know the hypotenuse. And I know that sine of theta is equal to opposite over hypotenuse. Let's see, opposite over hypotenuse, right? And so this one would be sine of 20 is equal to opposite, which is v sub y, over hypotenuse, which is 40 meters per second. But again, I'm solving for this velocity, so I'll multiply both sides by that 400. So we have 400 meters per second multiplied by sine of 20 degrees. That would give me my velocity in the y direction. Similar for velocity in the x, but instead of sine, we're going to use cosine because that is adjacent over hypotenuse. And what we end up with is 400 meters per second cosine of 20 gives us that velocity in the x direction. You may want to take a moment and plug in those numbers and get a final answer. I usually just leave it in that form and plug it in that way as I'm working through the problem. So let me show you what I mean. I want to know this height, so let's focus on the components in the y direction first. Okay, y initial. Well, initially, if the ground is my origin, if I establish the ground to be my 0, 0 point right there at the base of the cliff, he is starting 70 meters above the ground. The cliff has a height of 70 meters. So my y initial would be 70 meters. Y final, if this is my final position and that's my initial position, this y final is what I'm solving for. That's what I want to know. Velocity initial in the y would be the 400 sine 20. Velocity final in the y. How do we know that it's the top of the arc? And this is something we commonly forget. We forget that if I throw something up into the air, there's a point at which it will stop and turn back around. And in the y direction, that velocity slows down, eventually comes to a stop when it's at the top of its arc there, and then it will increase in negative y velocity as it approaches the ground again. So at this maximum height at the top of the arc, the velocity is 0 meters per second. We have an acceleration due to gravity, negative 9.81 meters per second squared, and we don't know the amount of time it took for it to go from here to there. So I'm going to look at my kinematic equations, and I'm going to pick an equation where I know everything except for this unknown that I'm solving for. There's two ways of doing this. You can solve for the time first and then use that to figure out the height, because remember later we're going to need to know that number. Or there is an equation that doesn't have time and we can solve for y final. Okay? I think it's about the same amount of work either way. Usually what I do is I use that equation that doesn't have the time component, and then I solve for it later when I need it later on in the problem. So I'm looking at my kinematics, and we have this kinematic equation. So it was velocity final squared equals velocity initial squared plus 2 times by acceleration multiplied by delta y, in this case because I'm in the y's, but it could be used with delta x. Let's recognize if any of these are 0. Let's see, this velocity final, that's 0. And then I'm going to solve for this y final. This y final is in a parenthesis, so I'll save that for last. This component is multiplied to these guys, and then this whole thing is added there. So that's the method I'm going to take to get to this number. I'm going to go exactly the opposite. I'm going to subtract this first, then I'll divide items out, and then I'll get into the parentheses. So I'll start there. I'm going to subtract velocity initial and the y squared. Now I'm going to divide by 2 and acceleration in the y. That's going to equal what was in the parentheses. And so now I'm able to get this by itself by adding y initial to the other side. Okay, awesome. Again, I would take a moment if you're following along with this. I'd hit pause, I'd plug in these numbers, and let's see if we get that same final answer. Okay. So when I plugged all this in, I'm going to write down my long number and then my rounded one for sig figs. Okay, so the longer number I got was y final 1023.95 meters, which is about, with 3 significant figures, 120 meters. That would be my final answer for part B here, but then I would use the long number later on in the other parts. Okay. B, C is really simple. C says, what's the potential energy of the hammer at the top of the arc? Okay, so it's asking what the potential energy is at the top of the arc. Now, potential energy, you find that equation on the board or in your equation sheet. It's mass times by g times by the height. Okay, and the mass of the object was the 60 kilograms of the hammer. We had that up above. G is just equal to 9.81 meters per second squared. And then the height at the top of the arc, we just solved for that. Okay, that is our 1023.95 meters. And I'm going to plug all of those numbers in, and then I got a long final answer of 602695 joules, and rounding for significant figures, I get 603,000 joules. Okay. Awesome. Okay, the next video I'll move on to part D.